This is video 5 on the series of videos related to Introduction to Statistics. And the topic of this video is deals with section 1.5.8, and it's on probability distributions. And this first I'd like to talk about discrete probability distributions. And well, actually, we've looked at a couple of probability distributions. They've both been discrete. And the one I'd like to talk about now is the binary probability distribution. So I've set up an example script which you can access on our website that shows the binary probability distribution. But first, I guess I should define what a probability distribution is. And to do that, let's see if I can get this. Not sure what's going on here. Okay, fine. So probability distribution, if we said P is our probability of, say, X, and for the binomial distribution, let's say X is the number of successes, the distribution describes how that probability changes versus X, which in this case was the number of successes. Okay, so going back to our example MATLAB script. So here is, this is a script that runs through the binary probability distribution, and let's set, here's n equals 50, so the number of tries is 50. Little p is the probability of a success, and in this case it's 50%. For example, if we're rolling, we're doing coin tosses. And X is the number of successes. Before we used R for the number of successes, but here I'm going to use X, and I'm varying X between 0 and n. So if we run that script, then we get the plot you see on the right, and this shows the probability as a function of the number of successes. And you can see with a toss of a coin, the probability of tails is highest. The highest probability occurs for 25 tails, for example, or 25 successes out of 50. And the distribution changes, of course, with the number tried, so I'll change it to 10 and run it. And you can see that the possible number of successes goes from 0 to 10, and the most probable number of successes is 5 for our case of our toss of our coin. So let's talk about some properties of discrete probability distributions. And in this case, the number of X varied from 0, 1, 2, all the way up to n. And it's discrete, so the changes in X are discrete. And in this case, the change in X was 1. So we would write, for example, the probability of 5 in our example here. Probability of 5 successes, and exactly 5 successes, is about, let's call it 0.25. And so 0.25, and this is in our coin toss example. And we could define the probability of the number of successes between 5 and, say, 10. And how do we do that? We, of course, can sum the probabilities where here I've denoted I as the probability of the I successes. And if we did that, we would find that the probability is 0.83. And relating that to the diagram, that's equivalent to the area of all these boxes going from 5 all the way to 10. And the probability of, what's the probability of all possibilities? What's that probability? Well, if you're thinking 1, then you're correct, because the probability of all possibilities is always defined as 1. So those are properties of discrete probability distributions. Now let's talk about continuous probability distribution. So the key with continuous probability distributions is the variable x can range from, say, x min to x max, but the interval between successive values is infinitesimal. So you can think of a continuous probability distribution as a discrete probability distribution in which the interval in the limit that delta x goes to 0. And we'll use dx as the infinitesimal interval between successive values of x. So in that case, we'll write little p of x, and that's not the probability of x. We would write the probability of x as little p x times dx. So this is the probability of x. So if we had a continuous probability distribution, what is the probability of getting a precise value of x? So, and the answer, if you're thinking, is 0. Well, it goes to 0. It's approaches 0, because dx is delta x approaching 0. Because it's extremely improbable that in a continuous distribution that you'll get exactly a given value of x. So when we assess probabilities, we assess intervals of probabilities. So the probability of x being between, for example, A and B, we would write that as an integral of little p of x dx, where x goes from A to B. And of course, what is the probability of all x? And of course, that's the integral from minus infinity to infinity of little p dx. And that by definition, again, is equal to 1. And little p is called the probability density function. And that is what defines the continuous probability distribution, or sometimes we'll refer to that as a PDF, probability density function. Now, an example of a widely used continuous probability distribution is the normal probability distribution, or it's the Gaussian distribution. So the PDF for a normal distribution is defined as little p of x is equal to 1 over sigma, which is the standard deviation, over the square root of 2 pi, times the exponent of minus 1/2 x minus mu over sigma, and that's all squared. And so this is, well, it's a Gaussian, and it's centered on mu. And just to note, this factor in front gives the integral from 0 to infinity of little p equal to 1. So we want to make sure that that integral always equals 1. So let's look at, for example, the probability distribution of, say, I don't know, a density, say a density of rocks here on Oahu, for example. And we might, if we did that, we might get something that looks like this. And, you know, the density might be something around 2.2 or something for heavy rocks on the surface here on Oahu. And let's look at a different probability density function. For example, the porosity of the rocks here on Oahu. And if we did that, we would get something that looks, if I plot this on the same scale, we'd get something that's, you know, very much smaller. So this would be, if this is 2.2, this is all less than 1, of course. It's even probably more confined to the 0 point than I've drawn here. So I'm sketching this out to show that the distribution, of course, depends on the units or what's being measured with respect what x really is. And you can imagine that, you know, these curves can have well, they do have an infinite number of sizes and shapes. But we can distill all that information by expressing the PDF in terms of a normalized function. So instead of using just plotting it versus x, we can plot the probability density function in terms of x minus the mean divided by sigma, right? In which case, both of these curves would look the same. So they would be centered on 0, and they would both plot on the same curve when the horizontal axis is z. And I forgot to write what's on the vertical axis of all these plots is little p, the probability density function. So in terms of z, the probability density function is equal to 1 over the square root of 2 pi times the exponent of z squared minus z squared over 2. And that's the probability density function for the normal or Gaussian probability distribution.